Perfect. All right. Another presentation later today that Christian is doing that I think you may be interested in. It's good.
I've highlighted a few that I definitely don't want to miss. So hopefully my meetings calendar doesn't get worse as the day progresses.
Yeah, it's funny. Christian took a look at the top data without, like, tried to block out everything else and didn't look at any of the conclusions we made, and ended up coming up with some conclusions that are fairly similar to the conclusions you made in your presentation. So
nice.
No, that was good.
It's not as abstract as it could have been.
Yeah, yeah, exactly. Yeah. Well, it is gorgeous weather out here in New Jersey right now.
Oh yeah, you are. That explains why Josh was behind your shoulder.
Yeah, yeah. Our Pierre, our CEO, is out here. We got a full week of meetings out here.
Nice.
Yeah, that's good.
So this is just one day out of many then.
Yeah, yeah, exactly. All right, we'll wait for another minute or two before we kick things off here.
Okay. And I assume at the end, Greg, you're gonna read some of the questions. Maybe I have a way of showing the chat here, but for now, I don't want it to get in the way of my the slide views.
I'll take care of the questions. You bet.
Okay, perfect.
All right, those of you that are joining, we'll be starting here in 30 seconds or so. Okay, let's kick things off. So I'm Greg Livingston with FluidTech, and I am very pleased to introduce our next speaker. Elona Rista is Product Support Manager at Solar Turbines and all-around turbine oil guru. And she will be presenting today and giving us some insight on temperature effects of turbine oil degradation and deposits. Take it away, Elona.
Thank you, Greg. Just a quick word, aside from your introduction. I guess I have been working for Solar Turbines for over 12 years now. And in the past few years, I have been delving deeper and deeper into all things lubrication oil, but primarily the field issues that we tend to come across. So the more I delve into it, the more my interest is piqued. And a lot of what you'll see today in slides is a direct outcome of the curiosity from the field cases that we encounter daily. So without further ado, I'll kick it off to some of the material that I've put together today, again on the temperature effect on turbine oil degradation and deposit formation. So first of all, I wanted to give you a quick overview of the test protocol that we have conducted in order to gather the data. This is the top test that is done by FluidTech. So as I told Greg earlier, he has a very special interest in this presentation because this is the data generated by FluidTech. We have collaborated for the past 3 or more years on this test, and what you'll see today is just a little sliver of the data that we have been able to generate on degradation of oils. But for this particular data set, the protocol that we followed is as follows. So for the 120 degrees Celsius test, which is the bulk of the testing that we have conducted to date, we take four 350 milliliter samples of new turbine oil. They are placed in a glass vial each, containing a steel and copper coiled wire catalyst, and then placed in 120 degrees Celsius solid black temperature bath. Dry air is bubbled through in order, again, to speed up the rate of degradation, similar to the role of the catalyst in here. And the test is lasts 12 weeks. And in that 12-week period, we take samples regularly. So we do a baseline test at time 0 for the oil. And then we take a vial out every 3 weeks. So at week 3, 6, 9, and 12, one of the vials is pulled out, and the typical routine analysis that we do for field samples is done on these units too, primarily focusing on the degradation parameters. So we're talking MPC, antioxidant levels, so Wooler and RPDOT, acidity level, so TAN, viscosity, and so on. In addition to this, we have conducted 2 other tests at higher test temperatures. So specifically, one 5-day test at 180 degrees Celsius, and another test at 195 degrees Celsius. And we only run these tests for 5 days because the degradation rate is much, much faster, as you will see in the next slide. So again, just a quick forward here on the thermal stress correlation so that we are all on the same page as to why one test lasts 12 weeks and another one is only 5 days. So the typical correlation that we see is the Arrhenius principle. However, there was an updated or improved correlation to this proposed by Consari and Boozer at Louisiana State University. According to their equation, there is, as you see here on the right side of the slide, the correlation between 65 degrees Celsius, which is the typical header temperature that we see in the turbo machinery operation. Once we place that oil from 65 degrees to 120 degrees Celsius, it is expected to degrade about 90 times faster by comparison. So the 120 degrees Celsius environment is 90 times more stressful. Once we move on to the higher temperatures, 180 degrees, that level of stress is much higher. So we're talking a magnitude of 3,700 times more than the typical header temperature of 65 degrees Celsius. And then 195, it's more than doubled compared to the 180 degrees Celsius. And so the question probably comes up, why are we testing the oil at such high temperatures, especially when the header temperature for turbo machinery, the oil coming out of the cooler is typically in the 60 to 70 degrees Celsius. What we are observing with increasing frequency is that higher temperature conditions in the lubrication system are not very uncommon. There are some conditions that maybe don't happen in every situation, but they are present in the field. So for example, we see cases of electrostatic discharge where much higher temperatures than what we are testing here, not 180 degrees and 195 degrees, but we're talking almost 1,000 degrees where electrostatic discharge occurs. Microdieseling is another event where such high temperatures are encountered. But once we bring it down to the temperature regime that we are that we are testing for here, we see situations such as where an oil heater is present, but it has poor temperature controls. The oil surrounding that oil heater might encounter the temperatures that we are testing for. And in addition to that, oil that is passing through the hotter sections of the turbo machinery, for example, in the bearings, certainly does get exposed to some of these higher temperatures. It is not the entire bulk of the oil that is sitting at that temperature the entire time, but those momentary exposures to this temperature do open the door to these degradation pathways that we will be discussing and seeing in the next few slides. So that is some of these situations are part of the reason why we are interested in the degradation mechanisms at these higher temperatures. So jumping right into some of the data that we have generated so far, oil 1 that you see here, like I said, this is just a little sliver of all the data that we have generated, but I've put up here some of the data that might be of higher interest. So as you see, we have the baseline for the oil at time 0. And then in column 2, this is at the end of the 12 weeks, the 120 degrees Celsius test. And then at the end of the 5 days of the 180 degrees Celsius test, and then at the end of the 5 days of the 195 degrees Celsius test. And you can see that the same oil is undergoing very different degradation levels throughout the test. At the baseline here, everything looks perfect. So the tan is low, the viscosity is normal. This was a 46 ISO VG 46 oil. The RPBOT is at 100%, and the MPC is negligible as we would expect it to be. In addition to this, one other component that we are bringing in aside from what we test for in the field is the deposition on the testing glassware, which turns out to be a very important parameter for us to observe, as you will see through the slides. It gives us some very important information. And so for this particular oil, as you see, after the 12-week test at 120 degrees Celsius, we see that most parameters are actually pretty healthy. We don't see much change in viscosity. Tan is within the margin of error of the baseline. Not much consumption of the antioxidants, but we do see the MPC increasing from 1 to 26. So we start to see, even at this lower temperature regime, we start to see some degradation mechanisms in play. And the MPC level is, so the presence of varnish is also confirmed by the amount of deposition that we see on the glassware itself, where not only is there coloring of the glassware, but we also see a certain amount of haziness, which tells us that there's a layer of varnish that has deposited on the glassware. Once we move on to the 5 days of 180 degrees Celsius test, this is where we start to see that the jumping from 120 to 180 degrees Celsius, even though we are stressing the oil for a much shorter period of time, the MPC is jumping up considerably. So we are accelerating certain degradation mechanisms much more. I apologize for the lack of vial and catalyst pictures for the 180 degrees Celsius test. Sometimes, you know, the data is too exciting not to share before all the information is in. But with the MPC data here, there is some confirmation that 180 degrees is more stressful than 120 degrees for the same oil. Then moving on to the oil at 195 degrees Celsius. So here we don't see much shift in the viscosity. However, this is where we start to see the acidity increasing considerably from the baseline. In addition to that, the consumption of antioxidants is at a much higher level. So we have dropped below the 25% threshold. And in addition to that, the MPC is also significantly higher than all the previous tests that were done. And in addition to that, one might argue that we have similar deposition of varnish on the glassware as well. As I mentioned, accompanied with a higher MPC test. So from oil 1, we start to see some inkling that the higher temperatures are harsher on the oil overall. And then we move on to oil 2, and that becomes much more clear that that is the case. So with oil 2, same test that we have conducted here, we see that for the baseline, again, this is a 46 viscosity oil. The tan is low as we would expect it. The RPBOT is at 100. The delta E is negligible. Right away, even with a lower temperature test, so the 120 degrees Celsius test, we start to see some of the parameters shifting considerably. We do see a considerable consumption of the antioxidants, so we have dropped in the 12 weeks of tests from 100 to 35%. And the MPC shows a drastic increase from 1 to 75, as evidenced by the photo of the patch, but also from the deposits on the glassware as well. So this oil doesn't seem to stand up very well to being tested at even the more mild temperatures of 120 degrees Celsius, but this becomes even more apparent as we move up through the temperature scale. So the 180 degrees Celsius test, I would say that the results here are somewhat similar to the 120 degree longer test. But moving on to the 195 degrees Celsius test, so we increase the temperature by only 15 degrees more than the previous column. And this is where we see a huge change in all of the parameters that we are showing here. So not only do we see a tremendous increase in acidity, the antioxidants are obliterated. The viscosity also seems to have undergone a huge change, which at least from a turbo machinery perspective, this would be very hard on the bearings and gears that rely on the specific viscosity of the oil at operating temperatures. Another very interesting thing happens at this temperature, where we all of a sudden see the MPC dropping from 81 that we saw or 78 that we saw in the previous test to 39. And in some cases, we do see this almost unexplainable drop in the MPC as we age or stress the oil more. And part of our understanding is that a lot of the varnish that we typically capture with MPC testing at times end up in deposition, so no longer in the liquid oil that we can measure through the MPC testing, but instead it ends up on the machinery. And as we can see here, the catalyst coil is looking much different than what it started. So a good bit of deposition on that, a good bit of deposition on the glassware as well. So even though the 39 MPC might seem a little more reassuring compared to 81 and 78, the rest of the oil parameters tell the real story here, that the oil is in much worse condition than it was in all the previous tests. Moving on to oil 3. So this is an ISO VG32 oil. We see that for the baseline, just like all the other oils, it looks perfectly healthy. With 120 degrees Celsius test, we don't see much change in the viscosity, TAN number, or RPVOT. We start to see a slight increase in the delta E, so the MPC patch. However, this is another example where the MPC is not really telling us the real story here. Because even though seeing an MPC of 8 is very reassuring for a fielded sample, the glassware tells us a different story. This oil, even at this very low MPC number, is showing significant amounts of deposits on the glassware. So while this oil was a little bit of an outlier on this aspect, we do see a range of responses for the various oils as to how the MPC correlates to the amount of deposition. We see some oils that at very high MPCs show little to no deposition on the glassware, and even though in the field that means a scarier MPC result in the oil analysis, realistically that is a better situation for the equipment. So moving on to the 180 degrees Celsius test. So again, here we don't see much change in the viscosity or the acid number of the oil, but we are starting to see the antioxidants being consumed due to the higher degradation that is happening at 180 degrees Celsius. In addition, the MPC has also risen considerably compared to the 120 degrees Celsius test. And then jumping on to the higher, so we increase the temperature by 15 degrees for the other sample. And this is where we see almost all of the parameters showing advanced levels of degradation. So viscosity doesn't change in this particular case. And correlation to the deposition on the glassware, where the MPC is actually comparable to the amount of deposition on the glassware and on the catalyst coil. Oil 4 here tended to do pretty well in terms of the 120 degrees Celsius test and the 180 degrees Celsius test, with some change
It appears like we are having a little connection issue, so we will wait here for another moment to see if Elona can join again. So my apologies for that. But in the meantime, Vanda's asked a question, an interesting question on oil number 3, and her question was that it's interesting to see the acid number decrease at 120 and 180 compared to new. And if I recall, I think the new acid number is 0.18, then it went down to 0.1. Elona, you're back.
Sorry about that.
Okay.
Apparently my connection is not as stable as I was hoping.
Okay.
Can you see my screen again?
Perfect. Good to go.
All right. Let me swap the screens, and here we are back. Okay, so hopefully you didn't miss some of my previous slides, but here we are on oil 4, where we are seeing some amount of degradation setting in at 120 degrees and 180 degrees Celsius. As we might expect, the antioxidants are being consumed, and the MPC is starting to increase as we go up in temperature. However, again, with only 15 more degrees, this is where we start to see all the parameters showing a much different picture. So we start to see a little bit of an increase in viscosity, a tremendous increase in the TAN numbers. Antioxidants, again, virtually all gone, and MPC is much higher at 70. This oil, however, is one that I mentioned earlier, an example of those oils that even though they show very high MPC numbers, the amount of deposition is lower. So by contrast between this oil and the previous one that we saw here, even though the MPC is a little bit lower here, you see that the amount of deposition is significantly higher than this, than oil 3, which with a slightly scarier MPC number, the amount of deposition is much more negligible by comparison. And just for fun, here's oil number 5, which was kind of a head scratcher, but also very exciting data to get back, where from the baseline, and again, I apologize, I don't have the 180 degrees Celsius data here, but even with the lower temperature test at 120 degrees Celsius, we see a tremendous amount of degradation on the oil. So pretty much all the parameters are showing us that this oil is in trouble. And by extent, the machinery with which it might be operating in the field. So we see a huge increase in the acid number. The RPVLT shows that the antioxidants are almost all gone. MPC is 60. However, I would argue that in both of these cases, in the 60 and the 52 for the higher temperature, it's a little hard for the MPC scale to assess which number it actually belongs to. And I've added here another parameter which we have tested for all the other oils, but in this case was much more prominent and much more meaningful, the weight of the residue on the patch itself. So for the baseline patch, as we would expect, it's negligible amount of residue, but as we age this oil, the patch seems to accumulate a huge amount of residue on it. So the oil itself, aside from the typical parameters that we measure in the field, seems to show a tremendous amount of deposition overall, which is, again, mirrored in the amount of deposition that we see both in the glassware itself, but also in the catalyst coil, aside from the MPC patch. So what do we learn from all this data, aside from it being so much fun to receive these pictures and these numbers back? First of all, that oil aging at 120 degrees Celsius, it does represent an accelerated version of reality for a lot of the field cases. So even though the bulk of the oil, and I'm speaking from the Solar Turbines perspective, the bulk of our oil is not sitting at 120 degrees the entire time, we do find out that the oxidative mechanisms that we get from the 120 degrees Celsius test are very similar to a lot of the samples that we are getting from the field. So there seems to be a pretty good correlation between our test and the field data. Obviously, we want to run our test in a shorter amount of time. We don't want to wait 5 or 10 years to get a sample. So we do try to age the oil at an accelerated rate. As I mentioned at least a couple times, is that standard testing doesn't always depict the reality in the field. So we get the MPC. I'll take MPC as one example. We get that MPC data, but sometimes an MPC of 70 might scare us to think that the condition is much worse than it actually is when it comes to the deposition of varnish on hardware, which again, from the turbo machinery perspective, that is the real measure of trouble, in my opinion. Once varnish deposits on the hardware, that's where it can cause the real trouble, not when it's circulating with the oil. And then we have the other cases where the MPC is telling us a delta E of 8, but we already start to see deposition occurring on the glassware and by extension on the machinery in the field. That is a much more scary situation for which we don't get the alert that we would like from the MPC test. In addition to that, the one good lesson from this is that accelerated aging at the higher temperatures does tend to create new degradation pathways. As we saw in more than one example, sharp increases in acidity, which we do see in the field. So we know that some of these degradation pathways are happening in real life, not just in these fun experiments that we are running. A rapid consumption of antioxidants, again, we do see examples of this in the field. Changes in viscosity, though rare, they do happen. And I tend to see it as a lagging indicator of severe degradation of the oil. And those cases of MPC rising and then unexplainably dropping even without any treatments, which might indicate that there is heavy deposition occurring, which is why the varnish is not showing up as much on the MPC patch. But unfortunately, in the field, for the field samples, there is no deposition test to mirror the glassware pictures that we get in this test. Hopefully, that is something that we'll get a test for in the near future. And since there were too many conclusions to put in one slide, here's another slide of conclusions. First of all, that not all oils are created equal. And as you saw, all these 5 oils, and actually our library is much larger than that. We have tested 20 to 30 oils so far. The way that temperature affects the oils, how much they age and how much varnish they create and deposit varies from oil to oil, even though we are subjecting them to exactly the same laboratory conditions. So this is a very good benchmarking exercise. The ranking or the performance can change from the temperature, as you can see here from the example on the right. So at the 120 degrees Celsius top test, oil 4 turned out to be the best one, had the least deposits out of all of them. However, when we crank up the temperature, all of a sudden, oil 4 drops to second place. So oil 1 seems to have a better performance at that higher temperature. And same thing can be said between oil 2 and oil 3. They swap positions in that higher degree temperature. Next is that deposition is a very high value measurement. And as I said, I very much hope that somebody is working on a deposition test that can be applied to field samples. Because again, from my selfish perspective as a turbo machinery engineer, I care what the MPC number is, but my real concern is how much varnish is actually depositing on the hardware where it can cause trouble. And lastly, and this question comes up very often with a lot of our customers, which one is the best oil? Which one do you recommend for us to use? And the answer is not as easy. It really depends on the application and the operating conditions. And this goes back to how some of these oils flip rankings when we change the temperature regimes at which they're operated. So the lesson there for me is that some oils that will perform perfectly fine at the lower temperature ratings might not be as well suited for those higher temperature regimes, and vice versa. So depending on what the operating conditions are for that particular customer and that particular equipment, the oil selection might change. And with that, I think that's my last slide here. I'll take any questions from the audience. And thank you for Greg for giving me this time and for everybody joining in.
All right, outstanding. Great presentation, Elona. And I think we only have time for, we have 3 different questions. I think we only have time for one. Vanda asked a question, interesting to see the tan decrease at 120 and 180 degrees. This is compared to the new oil, and I think she was referring to oil number 3. The acid number went from 0.18 maybe to 0.1 and then to 0.17. Do you have any explanation on what the reason behind that could be?
Yeah, in some of these cases, for example, I brought up oil 3 here. I don't know if that's the one that Vanda was talking about. But we see the tan changing a little bit from the baseline to the 120 degrees Celsius test to the 180 degrees Celsius test. I would say that when we are looking at these numbers, they are probably within the margin of error. So what I see from these, even though they are 3 different numbers, is that the tan has not changed appreciably with the 120 and the 180 degrees Celsius test. So I would consider these changes within the margin of error of the tan test overall. But in some cases, let me see if I can pinpoint the one that Vanda might be talking about. So yeah, pretty much all of these examples, I would say, from 0.18 to 0.1, we're still within that margin of error. I would expect the tan to be, in reality, to be more or less the same between the baseline and the 120 degrees Celsius test results here.
Excellent. All right. Well, thank you once again. That was fantastic. I got a lot from this and I love looking at this data, and I really appreciate this. Thanks so much for your contribution, and we'll see you at our next session.
Thank you.